Let's try to illustrate a matching M in a graph G and two vertex disjoint set M augmenting paths P1 and P2. So first, we have the current matching M, which are the edges V2, V3, and V6, V7, and we have the first M augmenting path P1, which are the edges V1, V2, and V3, V4. So this path starts and ends with the vertices that are not currently matched in M, which indicating that it can be augmented in matching. And we also have the second M augmented path P2, which are the edges V5, V6, and V7, V8. So similarly, it starts and ends with the vertices not in M and is disjoint from P1, meaning it doesn't share any vertices with P1. According to the corollary, if we take the symmetric difference of M with the union of the paths P1 and P2, we will obtain a new matching M prime that is larger than M by the number of disjoint augmenting paths. And since we have two disjoint paths P1 and P2, the new matching M prime will have cardinality of M plus 2 edges. The symmetric difference operation will add to the edges of P1 and P2 that are not in M to M prime, and will remove the edges that are already in M, which effectively flipping the matched and unmatched status of the edges along the both P1 and P2, since each path contributes one additional edges to the matching. The result is a combined increase in the size of the matching by the number of the paths, which in this case is 2. Let's try to represent a graph with a matching M and three vertex disjoint M augmenting paths P1, P2, and P3. And we have matching M, which is consisting of the edges V4, V5, V8, V9, and V12, V13. We have three M augmenting paths. P1 includes edges V1, V2, and V3, V4, and P2 includes edges V6, V7, and V8, V10, and P3 includes edges V11, V12, and V13, V14. The symmetric difference operator is associative, which means that the order in which you perform the symmetric difference operation doesn't affect the final result. Thus, you can take the symmetric difference of M with the union of all of the augmenting paths, like P1 union with P2, union with P3, union with blah blah blah, until union with PK, or just take the symmetric difference of M with each path individually, and then take the union of all of these differences. We take the symmetric difference of M with P1, P2, and P3 individually, and then we combine them due to the associativity gives us the same result. So as we take the symmetric difference of M with the union of all of the paths, the result will be a new set, which is M prime. Using lemma, we can add in each path Pi to the matching M through the symmetric difference operation, which can increase the size of the matching by 1, and since the paths are vertex disjoint, they are contribute to increasing the matching size independently. After we applying all k vertex disjoint M augmenting paths, the size of the new matching M prime is the cardinality of M plus k. This is because each path adds one additional edge to the matching. So for this graph, after we apply the symmetric difference to M with P1, P2, and P3, the size of the matching increases by 3, which resulting in a new matching M prime. Well, the cardinality of M prime is equal to the cardinality of M plus 3.